All right, for this next one, it's not an example problem. Instead, it's going to be a little derivation of another useful equation. So far we have two, and we're about to get our third. However, the third one doesn't carry any new information. It is derived from the two that we already know. In particular, it's useful because it describes the same type of motion that we've been talking about this whole time, but t does not appear. That's really useful when maybe you don't know anything about t and you're not asking anything about t. Time has sort of been this thing that we've had to use sometimes as like a crutch in between, where we have to say, okay, I'm trying to figure out how far I've gone. Once my speed has changed by a certain amount, well, let me figure out how much time it took, and then take that time and plug it into this equation and get the answer. And it works. But that hints that perhaps there's an interdependence that we can turn into a simplification. And here's how it goes. And you're welcome to follow as much or as little of the algebra as you'd like. We're going to start. Our interest is solve this equation for t. To isolate t, we subtract vi, v initial, from both sides. And we get v final minus v initial equals acceleration times time. We've already seen that back when we were defining acceleration. We saw these. Next, divide by acceleration. And so we have that time is equal to v final minus v initial divided by acceleration. And that's, of course, what we expect to see. That's how long you must accelerate for. Longer if the difference in your speeds is greater, and less long if your acceleration is greater. So that's what we expect, and it follows directly from that just by algebraic rearrangement. Now, if t is this, we can plug this in for t in this equation. Here and here. And we get d equals vi times vf minus vi over a. Do you see where that came from? We have the vi from here times vf minus vi over a. That's the t. Plus if we write vf minus vi squared over 2a. Let's see where that came from. Okay, well, it's over 2 because of the 1/2. And now there's a little bit of goofing going on, because we have t squared, which would be vf minus vi, the quantity squared, over a squared. But if we're dividing by a squared, and then we also have to multiply by a here, the result is simply multiplying by a, or dividing by a, right? This a cancels one of the squared a's here, because this a comes in the numerator, this a in the denominator is squared. The result is 1a left in the denominator. So this is the result of this term with t substituted in. Well, this is great. We already now have a rewritten equation for d, the distance covered, in a constant rate acceleration that doesn't involve t. However, it's a mess. Nobody can memorize it, and maybe we can reduce it, simplify it, and maybe even get some value out of that. Um, I'm going to first multiply every term by 2a to clear the denominators, because that is the most jarring ugliness. So we have 2ad, that's this times 2a, equals, if I multiply this term by 2a, the a gets rid of the denominator, and then I'm left with a 2. So I have 2 times vi times vf minus vi. And I multiply this by 2a, and so I get vf minus vi squared. It clears the denominator out. Okay, well, let's work on simplifying this more. We get 2ad equals, now I can distribute this to get 2 vi vf minus 2 vi squared. Can you see that? If we distribute this in, we get vi vf minus vi vi, which is vi squared, and I'm multiplying each of those by 2. So it's 2 vi vf minus 2 vi squared plus, now how do we do this? Vf minus vi squared. If you remember how to do, well, what's it mean to square something? It means multiply it by itself. So we do vf minus vi times vf minus vi. And you remember FOIL, where you do first, and then you do outer. You just multiply every combination, right? You remember that stuff? No, you don't. The result of that is we rewrite 2ad equals 2 vi vf minus 2 vi squared plus we get this times this, vf times vf is vf squared. We do, let's say, the inner term is minus vi times vf is minus vi vf. The outer terms is vi vf, so minus another vi vf. And then the last terms is vi times vi. They're both negative, so that comes positive. So that's plus vi squared. Now we just need to get out our cancel sticks and see what's left. Get 2ad equals, well, we have 2 vi vf minus 1 vi vf minus 1 vi vf. Will those all cancel? Okay. Now I'm left with minus 2 vi squared plus vf squared plus vi squared. Okay, great. We can simplify this more. I have a vi squared, and then I subtract 2 vi squared, which means I just have I'm left with minus vi squared, minus 1 vi squared. I have plus 1 minus 2. So I'll write the vf squared from here minus that remaining vi squared. And this is the useful equation that was promised at the beginning. Normally you'll see it written the other way around. Vf squared minus vi squared equals 2ad. Obviously it's the same thing written front ways or back. You can use this anytime that you could use the other two equations. It followed from them. But importantly, this tells you something about the direct relationship between the velocities and the distances under acceleration. We can see that the distance that we need for any given constant acceleration, we'll hold that constant. For any acceleration, the distance that we need to do that acceleration is proportional to the difference of the squares of the initial and final velocities. So if you increase the velocity difference that you'd like to achieve, you don't increase the distance by the same factor, you increase the distance required by a factor of the difference of the squares of those speeds. If we are talking about stopping distances, then Vf is 0, and this is just even more clear because it drops out some of the algebraic nonsense, and we have that the distance required to stop is directly proportional by a constant of 2 times our acceleration. The distance required to stop is directly proportional to the square of the velocity that we begin our stop from. And this is indeed why you go on and on lecturing 16-year-olds about not driving too fast.